This video lecture is about the life cycle of low-mass stars like the Sun, from birth to death.
Stars live for a very long time compared to human lifetimes. Your great-great-grandparents saw the same stars as you will see tonight. Our lifetimes are measured in years. Star lifetimes are measured in millions of years. In the previous lecture about star structure, you found that mass was an important quantity for determining what stars are like. In fact, all of the other aspects of a star, such as its luminosity, temperature, size, density, etc., can be explained using the fundamental property of a star, its mass. It is a simple calculation to find out how long something can continue consuming fuel. The lifetime equals the amount of fuel divided by the consumption rate. If your car has a full 15-gallon gas tank and it consumes 2 gallons per hour on the highway, then your car can travel for 15 gallons divided by 2 gallons per hour equals 7.5 hours. Stars are the same way. The amount of fuel for nuclear fusion is proportional to the total initial mass of the star. The consumption rate is simply the star's luminosity, so the star will live as a main sequence star for an amount of time equal to the mass divided by the luminosity. Recall from the end of the previous lecture that the mass-luminosity relation says the luminosity depends on the star's initial mass. So, the main sequence time is equal to 1 over mass raised to power p, where p is equal to 2 for the high-mass stars and p equals 3 for the common low-mass stars. If you put everything relative to the Sun in solar masses, it becomes the main sequence time is equal to 1 over mass to the power p times 10 billion years. Stars shine because of nuclear fusion reactions in their core. The more luminous they are, the more reactions are taking place in their cores. Massive stars live shorter lives than the common small stars because even though they have a larger amount of hydrogen for nuclear reactions, the rate of consuming their fuel is very much greater. The more initial mass a star has, the shorter its life will be. The massive stars are analogous to the big gas-guzzling SUVs with big gas tanks, and the small stars are analogous to the small gas-sipping hybrids with small gas tanks. The stages a star will go through and how long it will last in each stage also depend on the initial mass, with just a little bit of dependence on composition. Massive stars evolve quicker than light stars. The star life stages are analogous to our own life cycle. The gas cloud is like the womb, the protostar is the baby star, the main sequence stage is the healthy adult stage, the red giant is the elderly stage, the final outer layer mass loss is like our dying, and the core remnant is like the corpse. Next slide. Stars are born in giant molecular clouds, which are large, dense clouds of gas and dust that are cold enough for molecules to form. Each giant molecular cloud has hundreds of thousands to a few million solar masses of material, so from hundreds to many thousands of stars can be formed in these stellar nurseries. One nearby example is the Orion Molecular Cloud Complex that stretches from the belt of the Orion constellation to his sword, of which the Orion Nebula is a small part. The Orion complex is about 1,340 light-years away, and it's several hundred light-years across, and has enough material to form many tens of thousands of suns. Radio telescopes are used to probe the coldest parts of a giant molecular cloud. In the parts of a giant molecular cloud where very massive stars, O and B type, have formed, the hydrogen gas surrounding them can be made to glow in the visible band to make what is called an H2 region. The very hot O and B stars produce a lot of ultraviolet light to ionize the surrounding hydrogen. The electrons are knocked out of the hydrogen atoms. When the electrons recombine with the protons, they hop down the energy levels to produce emission lines in the visible wavelength band, with most of it at the red color of 656.3 nanometers. So the H stands for hydrogen, and the Roman numeral 2, double I, stands for hydrogen with one electron missing. The Orion Nebula is an example of an H2 region. It is the fuzzy patch you can see in the sword part of the Orion constellation. It is a bubble about 26 light years across that has burst out of one side of the Orion complex. Remember that massive stars form first and go through all of the stages of their life quickly. They don't live long enough to move away from where they formed. Furthermore, smaller stars are still in the process of forming, so H2 regions show us where stars are forming. Because of that, they are a very important type of gas nebula. For some reason, nearby supernova, spiral arm, density wave, etc., parts of the giant molecular cloud will start to fragment and collapse. The individual gas clumps collapse and heat up to form protostars. The gas clump becomes warm enough to produce a lot of infrared and microwave radiation. The gas clump forms a disk with a protostar in the center. Other material in the disk may coalesce to form another star or planets. Select the picture to bring up an image that illustrates the real power of infrared telescopes. You can't see the protostars in the visible band, left image, but you can see a lot of them in the infrared, the right image. A protostar will reach a temperature of 2000 to 3000 Kelvin, hot enough to glow a dull red, with most of its energy in the infrared. The cocoon of gas and dust surrounding them blocks the visible light. The surrounding dust warms up enough to produce huge amounts of infrared, and the cooler dust farther out glows with microwave energy. This longer wavelength light can pass through the dust. The infrared telescopes are able to observe the protostars themselves and their cocoons in dust clouds in our galaxy, while the microwave telescopes probe the surrounding regions. So, we use infrared and microwave telescopes for two reasons. Number one, the objects themselves glow in these wavelength bands, and two, those longer wavelength bands are able to pass through the dust. The bottom picture illustrates another important point about star formation. All the stars are born in clusters, and all the stars in a given cluster start forming at the same time. This is why we look at star clusters to test our models of star formation and life cycles. In some cases, the protostars are prematurely exposed by the strong ultraviolet emission and winds from nearby O and B stars. That means we can observe them in regular visible light. We see the dust disks in various alignments from our point of view. Planets can form from these dust disks. The Eagle Nebula is another famous star formation region with big gas dust pillars. The intense energy from a nearby star is eroding away the gas dust pillars to expose protostars at the tips of each of the tiny fingers sticking out from the edges, in a process analogous to how the hoodoos in Bryce Canyon were formed. The tiny fingers sticking out are each larger than our solar system. The next stage is the T-Tauri stage, so named after the first star we noticed going through this stage, star T in the constellation Taurus. This stage is sort of like the adolescent stage between childhood and adulthood for us. The temperature and density in the protostar's core becomes great enough to start nuclear fusion. The star turns on and produces strong winds that blow away much of the surrounding cocoon gas and dust. The dust gas disk channels the winds to flow preferentially along the rotation axis as jets squirting outward. With most of the cocoon gas blown away, the forming star itself becomes visible to the outside for the first time. The star settles down to being a calm, main sequence adult star. The star will spend about 90% of its life in the main sequence stage, which is why 90% of the stars are in the main sequence stage. It is fusing hydrogen to form helium in the core. This picture of the gorgeous Pleiades cluster at the shoulder of the Taurus constellation again illustrates the fact that all stars are born in clusters, and all stars in a cluster form at the same time from the same material. After a few orbits around the galactic center, gravitational tugs from other stars in the galaxy cause the stars in the cluster to wander away from their cluster and live their lives alone or with perhaps one or two companions.